Hello and welcome to Empowered Learning. This is the second video in the video series for finding zeros of polynomials of high degree. This particular video will be about the Karnas rule of signs, and what this is a procedure via a theorem that gives you an idea of how many positive and negative zeros a particular polynomial could have. And so in the grand scheme of things, what this particular theorem or procedure does, it allows you to be able to count the sign changes in each term, and then from that be able to get a rough estimate of how many positive and or negative zeros you could have. So this particular procedure or theorem, coupled with the rational zeros theorem that I discussed in the part 1 video, together works to kind of give you because lack of a better way to put it, it gives you a way to be able to cut down on the amount of work that you have to do to be able to figure out which rational zeros of a polynomial are actually zeros. Okay, so I'll kind of go through the process here, and then we'll see an example. So the process is basically this. So we're looking at two different things here. So first thing that we're going to look at are going to be the sign changes of our function f of x. And then we're going to look at the sign changes of our function f of x, but we replace negative x everywhere where we see x. That's basic idea here. So if we're looking for positive zeros, we're going to see where are all the sign changes that we have in f of x and come up with a formula to be able to do that. So we're going to count the number of sign changes in each term of f of x. And then once we count those total sign changes, we'll subtract 2 from that number and then do it again and then do it again until either we get 0 or a negative number. So as you can see in this example here, we have a total of 3 sign changes. Okay. So we go from positive to negative once, and then from negative to positive, that's another one. And then we go from positive to negative again, that's a third one. So here we know that sign changes are 3. So what we do is we start with 3, and then we subtract 2 from that, and we get 1. And of course, if we subtracted 2 again, we would get negative 1, but we can't count a negative number of zeros. So this doesn't make sense. And so what we say here is that based upon these sign changes, we will only have either 3 positive zeros or 1 positive zero. And so that's what these two graphs here are trying to convey to you. So how this works with the rational zeros theorem is that if we had a list of zeros that were here, and let's say, and I'll just make up a list right quick. So let's say from the rational zeros, we get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, okay? And so let's say we start off by trying all of the positive numbers here. And let's say we know that x equals 2 is a 0 of our polynomial. So what this lets me know, if let's say we try 1 and then we try 2. If we know that the 0, if x equals 2 is going to be a 0, then that is going to be the only one. That is the case when the possible number of zeros is 1, or we have to have 2 more, okay? And so let's say we try all of these positive 1, positive 2, positive 3, positive 4, and we see that the only 0 that we have here is x equals 2. Then what that's telling you is that the remaining 2 zeros that you have are either going to be complex conjugate pairs. So they're going to look something like this, or they're going to be irrational conjugate pairs. So they may look something like, let's see, a plus square root of bi, where b is not equal to a perfect square. Okay. So to kind of give you a concrete example, let's say this would be plus, positive 2 plus or minus I, or it'll be something like this. 2 plus or minus square root of 3, where square root of 3 is irrational because that particular number cannot be expressed as a fraction. Okay. So that's how the Karnas rule of signs helps you to be able to know from this list of possible zeros here, number one, are any of those going to work? If so, after we try some out, let's say all the positive ones, if we only get one positive one to work, then we know that if we have two remaining zeros, and they're either got to be complex or irrational. Okay. So that gives us an idea of the possibilities for positive zeros. Okay. And so, of course, here what this shows you is that with the sign changes, if we have 4, this is just another example. So here, since our sign changes is 4, we subtract 2 and get 2, subtract 2 again and get 0. So in this case, we know that if we were going to find the zeros of this polynomial, either it's got to have 4 positive zeros, or it has to have 2, or it has to have none. Okay. And again, using this along with the rational zeros theorem allows you to be able to know what to expect. So again, if we had a list, and I'll write list again here. So let's say we had the same list here. And let's say we had an instance where we tried all of the positive zeros here in this list, and we saw that none of them worked. Then we know that, hey, guess what? This lets us know that this is a possibility, okay? But also what this may mean is that you still may have 2 zeros or 4 zeros. It's just that these 2 zeros may either be complex, or they may be irrational, or you may have an instance where you have both a complex conjugate pair or an irrational conjugate pair, or you may have a case where you just have 2 of these irrational cases or 2 of these complex cases. So let's say you may have something that looks like this. You may have plus or minus 2i and -1 plus or minus 3i. In the case where all 4 of these zeros here are complex, it may look like this. In the case where all 4 of your zeros are irrational, you may have something that looks like this, plus or minus 3i and plus or minus 1 plus or minus square root of 5. So you may have this case as well. So again, this doesn't tell you exactly what the zeros are or how many you actually have. It just kind of gives you an idea of what the possibilities are. And again, based upon what we get with the rational zeros theorem, we kind of know a little bit more about what the zeros look like for our polynomial. So now that we've talked about how can we guess how many positive zeros that we may have, we can also talk about how many negative zeros we may have. And so like I said before, we use f of negative x to be able to do that. And so all we're doing is replacing x with negative x everywhere where we see x here. And what they essentially equates to is that every term that has an odd exponent on x will change sign. All of the other terms will keep the same sign that it had. And we see here that it only has 2 sign changes. And so because of that, what that lets us know is that either we're going to have 2 negative zeros, as you see here, or we're going to have none, okay? And so if we have none, then of course that means we have none. If we have 2, then that leaves the options open as to what that might be. So let's say if the rational zeros theorem for a particular polynomial gives us this result again, then if I find, let's say out of all the negative numbers, if I find that, let's say x equals -1 will be a 0, and let me erase this here. Let's try that one more time. All right, so let's say that x equals -1 is a 0. Then what that's going to tell me is that there's going to be another 0 that I have, and I know that it's going to be rational. And the reason I know that is because I know that rational zeros come in singles. So the only 3 choices that you have here is for your zeros to either be rational numbers, like what we have listed here. They could be irrational numbers, like let's say 2 plus square root of 7, something like that. Or it could be complex, which let's say this is like 2 minus 3i. And of course, in the irrational and complex cases, we have conjugates that actually go with these 2 types of zeros. So if I know that one of these zeros is already rational, then of course the other one has to be rational, because if I had another 0 that was either complex or complex here or irrational here, it would have to have another. Okay, and so the only way that this would not work is if, let's say, for the irrational case, if we did the, let's say, opposite of it, and it would actually be a positive 0 over here. Okay. Now for the complex case, there's no such thing as something being positive or negative, because complex numbers do not have order. So we couldn't even talk about that then. So my point here is that if we found a rational number that was a 0 for a case like this, then we would assume that, hey, you know what, there may be another one. And if it's not in this list here, then what that's telling us is that the other irrational, the other 0 that we're talking about is irrational. And let's say it'll be something like this, where the 2 minus square root of 7 would be the other -1, and the 2 plus square root of 7 would be the other one that's over here. Okay, and the positive 0, that would be taken care of on the other thing that we did, where we were counting the sign changes of f of positive x. Okay, and so in general, this is how we use the Karnas rule of signs to be able to just get a best estimate on the actual zeros that you do have for a particular polynomial. If you watch part 3 of this video series, you will see how we could possibly use the Karnas rule of signs to be able to sort of guess what we should try as far as using the rational zeros theorem when we go through that process of taking a polynomial and factoring it down to find its zeros and then writing it in factored form. So please check that out if that is something else that you need to know.